Hello and welcome to Wee's Studio. Today we're going to talk about cymatics and how it relates to the outer worlds. So there's some studies going on that are trying to view cymatics for wave propagation, and what they're trying to do is they're trying to analyze how you get specific geometries. So in some instances you can get different plutonic solids, and how those change and interact is not very well understood. There's been a little bit of research done on it, but there hasn't been done anything with like artificial intelligence or machine learning, computer vision, trying to analyze it in a way that a computer can understand. One of my long-term goals is to get someone in the field of computer vision to try to replicate cymatics in an engine like Unity, so that games can have very realistic water physics. Because right now it's like you see a ripple go out and it's like, that's not a real ripple. But what would be really cool is if you could see a drop of water fall and just emanate out, but then interact with every other droplet that's falling. And the boat that's going on in the background, and you see the bee land, and just seeing the propagation of all of those waves is a very beautiful thing, and can lead to very sacred things as well. Like the plutonic solids. But in trying to understand this, we need a lot of footage and a lot of different frequencies. We need to understand the properties of the dish, of the amplifiers, of the sound going into it, and the lighting and the alignment of the camera. There's a lot to consider when you're viewing cymatics, especially when you're trying to view them from an analytical perspective. It becomes very important to be at the exact center. With this micro slide, we can do that. And the other thing is to get the ring light perfectly aligned. So right here it's pretty well aligned, but there is a lot of discrepancies here. We will be improving this setup in the future with various different pieces of precision equipment that are made for optical systems. Because what we're really looking at in this thing is an optical system, and the applications of which are numerous at worst and endless at best. For instance, if you had a malleable lens on the front of your camera, a thin film that you could move back and forth, you could compensate for distortions in the air and get a very good telescope, or a very good camera that focuses on everything in the foreground. The scope is pretty vast in terms of what we can do with it. So, like doing active image stabilization, where that leads us is actually into bubble physics. I say bubble physics like it's a whole field of study. It is my field of study. We will be doing more bubble stuff on the channel because bubbles are really interesting. And they tie quite nicely into cymatics. Not only because it's a lot of the same equipment, but because instead of having a 2D plane that's oscillating, now we have a three-dimensional shape that is oscillating back and forth, that has a certain amount of surface tension to it, but a very, very little mass. And also, one of the fantastic properties of a bubble is that it has almost no compressive strength. So the only compressive strength it has is the inherent elasticity in it from the air that's behind it. So really we're just dealing with momentum. And that is a powerful thing that is not understood at all. If you try to look up physics on the oscillation of bubbles, it will lead you down a rabbit hole of vastly unrelated science. Like one of the things that I researched is actually there's a group of researchers, an international group that's trying to study the core of the Earth, and what they're doing is they're taking a massive sphere of molten tin and putting magnets around it and spinning it to try to replicate what's going on inside. And one of the things that they're noticing is that their container affects it very drastically, and they're getting various oscillations in the fluid that they weren't expecting. One of the things that they focused a lot on in that paper was the magnetic component of it, but there's also a very, very large frequency component to it that makes it so that the entire system is frequency dependent. So this spinning mass of molten tin, it's always going to be moving at a different rate. That's a given with fluid physics. But one of the things that they observed was when they let the system stabilize at an equilibrium point, they noticed that these oscillations would start to form different oscillations than what they predicted. So one of the things that they said was they thought they were going to have large transients going down the side, and then they would also have a difference in velocity of the orbit of it, or the rotation of it, and that would cause like stringing in it that would get longer and longer. They said that the test was inconclusive. They didn't let it run they didn't have enough data to say it with any certainty. But one of the things that they observed was that this change was affected by numerous amount of variables. But we're not going to be messing around with liquid tin balls and kiloamp magnetic fields. But we will be messing around with kilowatts and bubbles. That's something that I can do in this lab quite easily and have the capability to do right now. The limiting factor is actually the noise constraint of it, because in order to get a bubble to move visibly, you need a lot of displacement. One of the things that we find is that you need the driver of the speaker to move as far as you want the bubble to move, and we're trying to observe effects that are happening on the macro scale. So like we're trying to see millimeters here. We've observed that the bubbles can oscillate many inches, and when we take a DC component, like say a breeze or a breath, that they can move very far. But when you try to add an AC component to it, like a sound wave, we noticed that the amplitudes needed to achieve high frequency stuff, something above like 50 hertz, you need insane amounts of power to do that. But when you go down to say 10 hertz with a driver that can move 2 inches, now all of a sudden you can get very good coupling to the bubble, and you can see the bubble oscillate as the bubble moves on. and it's one of the ways that we can see sound move in our environment. Yeah, there's kind of two main areas that we're trying to push. The cymatic side with machine vision and getting very beautiful things out of it, and then the bubble physics trying to do a similar thing but in 3 dimensions. And one of the things with bubbles is we have a very convenient method to view the thickness of them based on the color of them. It doesn't necessarily translate to thickness precisely, but a difference in thickness over the whole thing. And we can also observe the age of a bubble like that. So after a given amount of time, a bubble will start to have a black tint to it. I'm not entirely sure why we have the black tint that happens after we get all of the color in it, but that's something that I want to investigate further, whether that be through scientific literature or by my own observations. So I'm going to start wrapping this video up. Please like and subscribe. This is an awesome channel. Please contribute. We don't have a Patreon yet. Let me know if you want a Patreon. And if you know an editor, an animator, if you're familiar with AI or machine learning or AI vision processing, please give me a shout out. Please let me know. Come help. I would be glad to assist in any manner I can as well. Thank you for watching.